So last time we talked about geocentric models. Now we're going to move on to heliocentric models. So heliocentric means the sun is at the center. And the first heliocentric model was done by Copernicus. And here's a diagram of his model. We have the Earth and planets orbit the sun in perfect circles. Now, that's going to explain retrograde this way, okay? Down here, this is the Earth, so we'll label that. And this is a planet, let's say it's Mars. And as Earth is moving in its orbit, it goes faster than Mars, so it passes it up. And you can see here that on day one, if I look at Mars, it lines up this way, and I would see Mars lined up with the stars over here. On day two, it's over here. But then on 3, it goes back to here, then 4, and then on day 5, it's over here. And if I was to follow the entire path of it from day 1 through to day 4, it's making this path like this. Day 1, day 2, day 3, day 4, and then back over here to day 5. So when the Earth passes the planet, appears back up. It's like when you are traveling in a car and you pass that car relative to you, that car ends up behind you, it ends up backing up. So what does this model explain? Well, everything's going to move around across the sky at 15 degrees per hour. But that's because this time the Earth that's because the Earth spins at 15 degrees per hour. All right, the sun is going to move through the zodiac because as the Earth goes around the sun is going to line up with different stars. When the Earth is here, the sun is lined up with the stars over here. When the Earth is here, it's going to line up with these stars over here. Same thing, because everything's moving, the planets are going to seem to move. All right, the planets do retrograde, we just talked about that. That's because they, when the Earth passes them, they seem to back up. It works on the change in apparent size of the planets because when Earth is here, Mars is pretty close, it's going to look pretty big, but when Earth is over here, Mars is going to look pretty small, so it explains that. It doesn't explain the change in size of the sun, because the sun is always the same distance from the Earth in this model. So other problems with this model is it still does not predict the position of the future position of the planets. Well, so people could say they still like Copernicus's model better. Okay. He also doesn't explain why we don't fly off a spinning Earth. In geocentric models, the Earth is just sitting still. Okay, in this model, in order for the sun to rise and set, the Earth has to spin, and we don't feel like the Earth is spinning. So what's going on? So the next person that came along was Copernicus. And Copernicus improved on, Kepler. Kepler improved on Copernicus's model. And the first thing he did was he had very, very precise measurements, and he found that the planets orbit in ellipses, not circles, with the sun at a focus. So now we can see why the sun appears to change size. If this is the Earth, when the Earth is closer to the sun, it's going to look bigger. And when the Earth is farther away from the sun, it's going to look smaller. His second law, when you read the words, it may not make a whole lot of sense. It says the planets sweep out equal areas in equal time. So if I think of a planet going around like this, okay, and I time it across A here, it covers this much area in a certain amount of time. And then in B, okay, it covers, in time B, it covers area B. And if time A equals time B, then area A equals area B. But the times are equal, the areas are equal. Now, one thing that is kind of important about that, for that to happen, all right, area A here is kind of short but fat, and then area B is long but skinny, okay, to make the areas be equal to each other. If that's true, it covers a lot more distance here than it covers here in the same amount of time. So what he found is that the planets move faster when closer to the sun. Now we know why that's true today, because of gravity, but they didn't know about gravity back then. And actually, when Newton came up with gravity, he knew about this idea, and that was probably some of the way he figured out about gravity. The third law is a mathematical one, and it says t squared over r cubed is a constant. I'm going to add to this a little bit. All right. Where t is the time to go around for the planet, and r is the radius of the orbit. So what this is saying is t squared, t is the period, and I square it, I divide it by the radius cubed, I get a constant. Now that doesn't make a whole lot of sense until you see it once. So I've got some data here for Earth and for Jupiter. And the units, time makes sense, is 1 year. It takes the Earth 1 year to go around. The distance, r, the radius, is in AUs, and that's the distance from the Earth to the sun. So the distance from the Earth to the sun is 1 AU. So if I do this, I do t squared. Well, t in this case is just 1. I'm going to square it. And 1 squared is just 1. And then r cubed. Well, r was 1 in these units too. So r cubed is going to be 1 cubed, and that's also equal to 1. I'm going to divide those two things, and I get 1 divided by 1 equals 1. So that was pretty simple. Now it says it's supposed to be a constant, so if I do it for any other planet, I should get the same value. I should get 1. So looking here, I've got the data for Jupiter. Jupiter is 5.2 AUs away from the sun. That means it's 5.2 times as far as the Earth. And the time it takes for Jupiter to go around is 11.86. So t squared, t is 11.86. I'm going to square that. And that's going to equal 140.7. And then r cubed, I'm going to take the r value here, this 5.2. I'm going to cube that. And that's going to give me 140.6. Divide those out. I get 140.7 divided by 140.6. And that gives me 1.0007. Almost exactly the same. And he found out that's true for any planet in the solar system. So what does this explain? Okay, it's going to explain everything, so we can check off all of them. All right. So this was a great model for two reasons. It made specific mathematical had a little trouble with that. Let's go. Made specific mathematical predictions which could be tested, and they will always pass the test. And the second really important thing is that this predicts the positions of the planets very accurately. So we still have the question, why don't we fly off base plan Earth? All right. And Newton came along and answered that. By discovering gravity. Okay. Explains a few things. Why we don't fly off. Explaining Earth. And planets move faster. And closer to the sun. And again, I was saying that he knew about Kepler's rules, and part of the way he came up with gravity is kind of thinking about those rules.